All right, so it's 2 o'clock Eastern time now. Maybe I should get started. So hello everyone. Hello people from Penn State, from Akron, from San Diego. So this is so cool. I can talk to all of you at the same time. And first of all, I'd like to have a short introduction of myself. So as you can see from the slide, my name is Yang Zhang. I'm from University of Illinois, Urbana-Champaign. So this is my second year as assistant professor, and before that, I work at the spallation neutron cells at the Oak Ridge National Lab. Okay, so is the sound good? Can everyone hear me? Great. Okay. So so I work at Oak Ridge National Lab for 2 years, and before that I was a graduate student at MIT. So I now see my supervisor is also here, Professor Shaoxin Chen, and also Professor Jean Stanley is also here, who was on my thesis committee. So a lot of my thesis work have been focused on studying supercooled water, actually under confinement, with neutron scattering. So I'm so happy to see both of them here today. So, well, thanks to Jin's nice talk the day before yesterday, I can start what he has left, to talk about the general properties of liquid, supercooled liquids, and gases. So if everything's okay, I think I'm gonna get started. Good. Okay, so today I'm going to talk about the general properties of liquid, supercooled liquids, and gases. So as you can see, I changed a little bit of title from in the original syllabus. In the original syllabus, I put the title "Supercooled Liquids and the Glass Transition." So why did I do that? So I thought about that a more appropriate title. So everyone talks about the glass transition, but you'll see throughout the talk, glass transition is really not an equilibrium phase transition. And to make it clear, I removed the word the word transitions. And then I thought about, to talk about supercooled liquids, maybe I should also mention a little bit something about liquids. So liquids is really the stable state, and supercooled liquid is actually the metastable state, and glass is the non-equilibrium state. So when putting these three together, we have a complete description of this disordered state of matter. So that's why, that's a little bit motivation. That's why I changed the title to be liquid, supercooled liquids, and gases. Okay. All right. So now before I get started, I need to make a disclaimer. So obviously, this topic is huge. It is impossible for me to cover everything in liquid, supercooled liquids, and gases, in a lecture of this length. So on one hand, this field is too big to capture it all. On the other, a lot of key questions remain to be answered. So although people have been studying liquid for a very long time, and a lot of important results have been found, but still, we do not have a theory that can predict the properties of liquid. And we don't even have a coherent picture of water yet. So, in this lecture, I will try to focus on aspects that are relevant to neutron scattering experiments. So I'm an experimentalist, and I want to look at the theories of liquid, supercooled liquids, and gases from experimental point of view, particularly from neutron scattering. If you look at the history of liquid state physics, now a lot of the results are based on neutron scattering. Actually, two important techniques advanced the development theory of liquids. One is a neutron scattering. The other is atomistic simulations, like molecular dynamics simulations or Monte Carlo simulations. And later on, you will see neutron scattering can be directly compared with these atomic simulations. That's why making neutrons a very unique tool to study the properties of liquids, supercooled liquids, and gases. Okay. So like always, I want to start from this beautiful picture. And the reason is what I see from this picture is a phase diagram. So I'm sure you have seen this phase diagram from Jean's talk. So from this picture, you can see that nature is very complex. We have a solid ice floating on top of this liquid seawater, and in the air there's also water vapor. So it's very amazing. Not only this picture looks amazing, but also the physics is amazing. So if you think about that, all these complicated phase diagrams are only composed of only one species of atom. In this case, it's water. So with one species of atom or molecule, you can already have such complicated phase diagram because of interactions. So at low pressure, high pressure, and high temperature side, let me use the arrow. So at the low pressure, high temperature side, so the interactions between the molecules are so weak, so they form a gas. So basically, there's no interactions, and the gas can be quite well described by the laws of ideal gas. I'm sure that you have learned this in college physics or even in high school physics. Okay, and then when we lower the temperature or go to higher pressure, then we can enter the solid state. Solid state is relatively simple, although it's a little bit more complicated than gas, but still simple. Because in a solid, usually when we mention solid, we imply it's a crystal. So all the atoms and molecules are arranged in a periodic fashion. Okay, and of course there might be some different kind of orderings, but all of them are basically periodic. They can describe by groups, and so they have long range order, and a lot of development have been made in the study of solid. So that's why in almost every university now you can take a course on solid state physics. But in between solid and gas, liquid is rather complicated. Okay, so as you can see, we have a course on solid state physics, but we don't have a course on liquid state physics. Okay, and the reason is we don't really know enough about liquid, unfortunately. So if you look at the molecular atomistic picture of liquid, at very short time, liquid behaves very similar like a solid. Every particle is just rattling, and they don't really travel far away, just like a solid. But if you look at the long time scale, all the particles will diffuse to very far. That's why liquid can flow. That's more like a gas behavior. So liquid is actually more between, well, not only you can see that from this phase diagram, but also from a molecular picture, liquid is really between solid and gas. The reason we have liquid phase is really because of this delicate balance between these adhesive forces between molecules and also the entropic force. So in order to understand liquid, we need to basically describe have a theory that can take into account this long time scale behavior. Okay. This is even more striking in the supercooled region. So there are a few more things that I want to mention in this phase diagram, and they'll be relevant to the rest of the talk. So the solid lines here, there are three solid lines. This red line, blue line, and green line. They are the first order phase transitions between the different phases: solid, liquid, liquid gas, and solid gas phase transitions. And so the three phases coexist at one point. This is so-called the trickle point. Okay. So according to Gibbs' phase law, we know that for the three phases to coexist in the PT plane, there's only one point. It cannot be a region. The degree of freedom is basically zero. There's no other point that the three phases can coexist. So the temperature and pressure of this point is uniquely determined by the molecular properties of the molecule. Okay. So in the case of water, so if I can ask a question, so do you know how the trickle point is used? So basically, our temperature scale is determined by the trickle point of water. So we're actually using the properties of the trickle point of water every day. Okay. The next point that I want to mention is this critical point. So when we go to high pressure, high temperatures, the first order phase transitions between liquid and gas kind of disappeared, and the end with a critical point. Beyond the critical point, in this region, so-called supercritical region, there's basically no difference between liquid and gas. Okay, and the phases can continue to change from liquid and into the supercritical region, and then to the gas phase. But on the other hand, the liquid solid phase transition line does not end with a critical point. So as you can see, there's a lot implied in this phase diagram. It's very complicated. Actually, I'm really amazed that nature behaves this way. And again, let me try to remind you, this is only a phase diagram for one species of atoms and molecules. And actually, for many of the systems, these tend to show universal behavior. A lot of substances have such a phase diagram. Okay, so now I'd like to ask a question. Actually, in this the phase diagram I draw here is actually not a phase diagram of water. So does anyone see what's wrong with this phase diagram? So if you can type, maybe you can type in the chat box, or if you can raise your hand, maybe we can talk to each other. We have a winner, Oli. So solid, thank you very much. The solid liquid transition has a positive gradient. So for many of the substances, the liquid solid phase transition has a positive slope. And the reason why I have positive slope is because of the Clapeyron equation. And when the slope is positive, it means that when liquid crystallizes into a solid, the volume shrinks. But for water, it's actually the other way around. When water crystallizes into ice, water expands. So, or in other words, the density of ice is less than the density of liquid water. Actually, that's why we have such a beautiful picture on the back. Otherwise, the iceberg will not be floating on top of the sea. They will be sitting at the bottom of the sea. Okay. So again, this phase diagram is truly amazing. So I always, every time I look at that, I was thinking, if I were the god, I wouldn't design a phase diagram that is so complicated. Okay, so I saw another answer: glass transition not shown. Okay, so glass transition is as I said earlier in the talk, it's not really a phase transition. So here in this so-called phase diagram, what I showed here is the equilibrium phases. But we'll go to the glass transition very soon. Okay, so since we talked about glass transition, we should mention this. The liquid-solid phase transition line, the first order phase transition line, actually can be bypassed from the liquid state. So if we cool down a liquid careful enough, or if the liquid is very pure, or there's no external perturbation, so sometimes we can enter the solid region of the phase diagram, but without crystallization. And this phenomenon is so-called supercooling. Okay. And the same thing if you go to, if you want to cross this liquid gas phase transition line. If you go from the liquid phase and carefully to the gas phase, you can also get a metastable phase of liquid on the gas phase side. So this phenomenon is so-called superheated liquid. So the region of liquid, the region we show here in this phase diagram is the stable phase of the liquid. But we can certainly extend these phase boundaries and go to the metastable phase. And those are the so-called metastable phases of water. So in this talk, we'll focus on the supercooled liquid, not the superheated liquid. Superheated liquid is relatively easier to understand because temperature is high, the system is ergodic. So although it's a metastable state, but it's relatively, the dynamics fast, so it's easier to understand. But for the supercooled liquid, the dynamics is very, very slow. So, and if you keep going down, and eventually they will form a glass. Okay, so I saw one question here, and it's from Yu Zhang. And let me try to repeat the question: is why water doesn't have superheated liquid? Okay, so water does have what is superheated liquid. Okay, so both the supercooled liquid and superheated liquid are metastable states. And so when I started working on water a couple of years ago, and was first introduced this concept about supercooled water, I was really wondering, how to make such a supercooled water, and does it really exist? Okay, so I tried a homemade experiment by myself. So and this was in my dormitory before, and let me turn off the error. So I want to show you what does a supercooled water look like before we go into the theories. So Mei Yun, could you please help me to play the video? Thank you. Hello, my name is Yao. Today I will show you a demonstration of supercooled water. So here's the bottle of water. Tap the temperature overnight. The temperature is below 0 degrees Celsius. But I can see it's still liquid. However, a small modification will trigger the relaxation. Now let's see. Wow, that's unusual. So the sound quality was poor. So at that time I didn't have iPhones. This is just videotape with a camera. So, but I can try to explain again. So basically, I just put a bottle of water. It's basically unopened and put it in the fridge and try to lower the temperature below 0 degree. And you can see that as the temperature is below 0, the water still remains as a liquid state. They can still flow. But when I open the bottle and try to shake it, it's suddenly frozen. So supercooled water is really a metastable state. It's not the stable state of at that condition. The stable state is always the crystal, which is the ice. So if you prepare water careful enough, we can have this supercooled water. And actually, that's not that difficult. We can do that at home by ourselves. So if you want to see that again, you can go to YouTube and search my name and supercooled water. Okay, so let's continue. So now, oh, I saw there's another question from you. So the question is, what kind of situation makes the water become superheated? So that's a very good question. Thank you for asking. So superheated water is actually much easier to make than supercooled water. Supercooling, you have to try. Well, if the water has some impurity, they will crystallize. So you may have to try like a bunch of bottles of water and to make one bottle of supercooled water. But superheated water is actually much easier to make, and maybe you have already been making that. So one way to make it is actually to use a microwave. Okay, so if you put a glass of water in the microwave and heat it, and the temperature of the water actually can go above 100 degrees Celsius. The water remains as a liquid state. And this is actually very dangerous. I warn you not to try that at home, because if you do, if the water is superheated, if the temperature is above 100 degrees, but if you give it a little bit of perturbation, sometimes a shake or add some sugar or salt, or even put a spoon inside the cup, the water will explode. So again, I'm sure you can find some demonstrations from YouTube. So try to remember not to use microwave to heat water. Otherwise, water will be superheated. Okay, so let's continue to talk about this metastability. So water, both the supercooled water and superheated water are metastable states, as I mentioned. And I showed you, like with a certain perturbation, then they will always go to the most stable state at that condition. So for the superheated water, they'll become water vapor. For the supercooled water, they'll become ice. Okay, so to understand the metastability, it's useful to consider this energy plot, energy as a function of coordinate. So at the moment, you can think of the x-axis is just the some coordinate of the system, like position maybe, or if there's only one particle. Okay, so in this energy curve, I plot two minimum. Okay, one is a deeper minimum, the other is lower minimum. So we know that if the system is at the lowest minimum, it's a ground state, then the system is the most stable. But sometimes, if you cool down the system may get trapped into some local minimum. Okay, local minimum. So if you do not touch it, and it will take a very long time, sometimes infinite time, for the metastable state to go to the ground state. And for that to happen, of course, the system has to overcome certain energy barrier. Okay, if the activation energy barrier is huge, then it takes a very long time for the metastable state to go from to go to the ground state. Okay, so a simple picture would be if you can imagine, if I were just have a ball and put it on certain surface. You know, naturally, the ball always wants to go to the ground state, but sometimes it gets stuck at the metastable state, and that's how you have a metastable state. Okay. So there are many examples of metastability around the world. So I've given like two before: supercooled water and also superheated water. They are supercooled state. Actually, there are many more examples around us. Some of them are just macroscopic phenomena, like avalanche. Okay? So the snow itself is in the metastable state. If there's certain shock, and they will go to the ground state. So other metastable phenomena include supercooling, as I demonstrated, and also superheating, like microwaved water. And there's another phenomenon related to water, which is also metastable state. This is a so-called supersaturation. So sometimes when the weather is very wet, but still doesn't rain because there's the air is supersaturated, but there's no nucleation site, so there's no rain. So all these phenomena are related to metastability. So metastability itself is a very intriguing idea, and itself worth a lot of study. So a lot of materials around us are actually metastable. So I'd like to show you one picture. So a comparison of diamond and graphite. And we know that both diamond and graphite are just carbon atoms. There's nothing more than that. So in fact, diamond is actually the metastable state. Graphite is the stable state. So if you have a diamond and leave it there for a very long time, maybe billions of years, it will eventually transition into the stable graphite. Okay, so some people say that diamond stands for eternity or forever. So actually, graphite is more stable, much more stable. Okay. Now we can start to talk about the glass transition. Since we mentioned the stability, so liquid itself is a stable liquid, and if under certain conditions we can drive the system out of equilibrium and go to the metastable state, and if we keep doing that to the extreme, then we end up with a glass state. So in the case of water, if we supercool like the way I did with the fridge, then I can form a supercooled water. But if I do it really fast, then before water can crystallize, the kinetics become extremely slow. Water can form a glass. So many materials can form glass. Okay. So in this slide, I want to talk about the thermodynamics of so-called glass transition, or in other words, the heat capacity. So heat capacity is very important because heat capacity basically describes the entropy fluctuations. Okay. So in this slide, I show you 4 glass forming liquids. The first one, A, is a molecular level liquid toluene. And second one is a metallic system. It's gold silicon. And third one is a covalent compound. And the last one is a open tetrahedral network, germanium oxide. It's actually germanium oxide is very difficult to crystallize. So as you can see, when we try to measure the specific heat capacity of a material as a function of temperature, so as the temperature is lower, let's look at the figure A. So when the temperature is lowered, if the crystallization is avoided, we can still have a change of the heat capacity near around Tg. So the glass transition actually is defined at the inflection point of the specific heat. So we can measure specific heat with something like differential scanning calorimetry measurement or some other instruments. Okay, so a lot of them seem to show universal behavior. So the specific heat shows a significant change, but it is still a continuous change. If the specific heat shows a discontinuous change, then this would indicate a first-order phase transition. But glass transition itself, the so-called glass transition, is not a first-order phase transition. So you can see the specific heat still changes continuously, but definitely there is something going on. It looks like a second order, but actually some theories try to explain the glass transition as a second order phase transition. But still, most people believe that the glass transition is not a true thermodynamic phase transition, but rather a kinetically trapped phenomenon. So later on, you'll see that for the first three systems, A, B, and C, the specific heat jump around the glass transition is actually huge. But for the last one, it is small. So for the first three, they're actually so-called fragile liquid, and last one is called strong liquid. So for the strong liquid, examples include germanium oxide or silicon oxide. They tend to form open tetrahedral structure, similar to ice. Okay. So now, if we integrate its heat capacity, well, we can get enthalpy. So in the next slide, I want to show you either entropy or enthalpy or volume. So we can plot all of them versus temperature. So if we start from a liquid, when we cool down the liquid, at a certain point, most of the time, the liquid will undergo a first-order phase transition and crystallize into a crystal, like here. So, so Tm here is the melting point, melting temperature. So when the liquid goes into the crystal, and the entropy or enthalpy or volume of the system just follows the crystal behavior, this bottom line from here to here. Okay. So now, if we cool down the liquid careful enough, so we have mentioned that cooling down careful enough is actually more complicated than just saying. So how do you cool careful enough? There's a lot of phenomenon going on. Try to avoid this first order phase transition. Really depends on like the nucleation rate or the crystallization rate of the material, and its comparison between its relaxation time. But that is obviously beyond the scope of this talk. So let's just say we can avoid this first order liquid to solid phase transition, and we can go into this metastable supercooled liquid regime. Okay, and if we keep doing that, and eventually we'll hit the so-called glass transition temperature. The glass transition is defined in several ways. In the previous slide, we showed that glass transition is defined at the inflection point of the specific heat capacity. So here, what basically coincides with that inflection point. Or in other words, you can also define the glass transition from a dynamic point. We'll mention a little bit more in the next slide. But here, you can already see that it's defined by the relaxation time. So in this paper, the authors say that the glass transition is defined at the relaxation time is approximately like 1,000 seconds. But usually we try to define this relaxation time reaches 100 seconds or in terms of viscosity, is 10 to the 13 points. Okay, so but as you can see here, I have several lines near the glass. So it means that depending on your cooling rate, you may end up with a different glass state. So glass is not unique. It depends on the thermal history, how you define the glass transition. So if you cool it down fast enough, then you can actually reach the glass transition at higher temperature. If you cool it down slow enough, then you can go to an even lower glass transition temperature. So fortunately, when you change the cooling rate, okay, the glass transition doesn't really change much. Glass transition always lies in a very small range, although it's really not, again, it's not very well defined. It depends on how you cool the system, how to prepare the thermal history of the system. But roughly speaking, you can define the glass transition around this temperature. And the typical cooling rate is about 10K per minute or sometimes 20K per minute. They won't change your glass transition temperature a lot. So let's go. Let's see. So next temperature that I want to mention in this figure, which is not very obvious, is so-called crossover temperature. So this actually happens above the glass transition and in between the melting and the glass transition temperature. So for crossover temperature, this will be the onset of the so-called activated process. So above this temperature in this region, the dynamics of the material is still dominated by the self-motions. And a certain onset temperature, so-called crossover temperature, the activated process, or many people in different describing this term in different theories. Sometimes it's called cooperativity, cooperatively rearranging regions, or sometimes dynamic heterogeneity, or hopping. So below this temperature, those phenomena start to occur. But if you just look at the entropy or enthalpy of the specific volume of the system, there's no clear transition. Okay, so this is not a transition either, but actually from the dynamics, you can see there's a clear change here. So the crossover temperature is oftentimes underestimated. A lot of people talk about the glass transition temperature, but nowadays the opinion becomes the crossover temperature is probably as important as the glass transition temperature, in the sense that crossover temperature is more well defined, and a lot of phenomena happens at the crossover temperature. So the last temperature that I want to mention in this figure is here. This is so-called Kaufman temperature. And the reason is that when people first study the entropy of the system, so in the liquid state, before reaching the glass, we can extrapolate this line. So if the glass transition does not happen, if gas transition doesn't happen, so the entropy should keep going and eventually hit the crystal. And if you go below this temperature, below the so-called Kaufman temperature, the entropy of the glassy state would be lower than that of the crystal, which is against our common belief. So we always believe that crystal has the lowest entropy. So crystal is always the ground state. But by extrapolating the entropy of the liquid, we can get a Kaufman temperature. So it's also called entropy crisis, sometimes also called Kaufman paradox. It's basically at the temperature when the entropy of a supercooled liquid or glass becomes the same as a crystal. So when we go below that temperature, then it's against our basic sense of thermodynamics. Okay, so in order to explain this Kaufman paradox, so obviously, we can assume that above this temperature, underlying thermodynamic phase transition has already happened. So there might be a unique state of glass, so-called ideal glass state. Okay. All right. So now I see another question from E. The question is, how fast or slow one has to cool to obtain a crossover temperature. Okay, so actually, it doesn't really matter like how fast or slow you cool down. So the crossover, the other reason why crossover phenomena is more important is that in this temperature range, the system is metastable. So it's still near equilibrium. Okay, so you can, so ideally, it doesn't matter how you cool down the system. You can always get the same crossover temperature. But for the glass transition, that is different. The glass transition is really a transition from a Gaudic state to non-Gaudic glassy state. So that depends on the cooling rate or the thermal history. The crossover temperature is more like a thermodynamic crossover phenomena. So it doesn't really depend on the cooling or heating rate. Okay. All right. So let's go to the next slide. So we have talked about the thermodynamics of glass transition. So now let's move on to the dynamics of the glass transition. So in this slide, I show you the viscosity versus basically versus 1 over temperature. And we show that in the log scale. And because viscosity changes several orders of magnitude as the temperature is cooled towards the glass transition. So this figure summarizes like almost around 20 glass-forming liquids. Some of them are molecular, some of them are organic, inorganic, metals. So you can see that although the glass transition temperature is different, but the glass transition temperature almost uniquely defined as when the viscosity reaches 10 to the 13 points. And so as a physicist, we always want to try to find the universality between different materials. Just like the universality or scaling laws near the critical point. So for the same reason, we want to find some universal scaling behavior of all the viscosities. So it's natural to think about how to scale the temperature here. Now we use 1,000 over T is basically 1 over temperature. So one trivial temperature to scale this figure would be to use the temperature at the critical point, right, which is uniquely defined. And also you can use the temperature at the triple point, which is also uniquely defined to do the scaling. But unfortunately, for many of these materials, it's not easy to get the triple point or critical point temperatures. Well, at least we cannot get all of them. So, but this temperature is very close to glass transition temperature, and we know the glass transition temperature by experience. So, what we can do is scale this temperature with their corresponding glass transition temperatures, and that gives this famous plot from Austin and Angel. So if we plot the log of viscosity versus Tg over T, and most of the materials fall into basically two categories. So for one category is so-called strong. It's basically very close to a straight line. So log of viscosity versus 1 over T, the slope would be basically the activation energy, as I mentioned in the previous figure of the metastability. So for strong material, then the activation energy is basically constant or independent of temperature. For the other class of material, most of them, the activation energy increases as the temperature is approaching the glass transition temperature. And if we compare with this inside specific heat, we can also see that these strong materials like germanium oxide has a very small change in the specific heat near the glass transition. But for all the other fragile materials, there's a huge specific heat change. So the strong materials are defined by if the viscosity follows so-called the Arrhenius behavior. So viscosity is proportional to the exponential of activation energy divided by kBT. So in this case, if we take the log of viscosity and plot log of viscosity versus log of T, the slope would be the activation energy. And for this behavior, it's clear to see that the viscosity goes to infinity when temperature approaches 0. And for the other class of materials, the fragile materials, we can usually describe them with so-called VFT formula. So it's Vogel, Future, Taman. So they first found out for a lot of material, the viscosity can be described as exponential, very similar to the Arrhenius behavior, but diverges at a finite temperature T0. So when T is equal to T0, viscosity becomes infinite. Okay. So there's a clear difference between this strong material and fragile material. And based on this, we can also define so-called fragility. Fragility is basically the slope in this Arrhenius plot at the glass transition temperature. So the slope at this point. So it's amazing that for many glass formers, we can define the fragility, and most of them follow these two fragile to strong patterns. But it is still open question, like how to explain those fragile to strong behavior, fragile and strong behavior. And so what molecular architecture or kind of interaction can give rise to this strong or fragile behavior. So most of the strong materials are like open tetrahedral structure, like silicon, silica, germanium. So, but we still don't really have agreement on like how to describe the fragility of material. So previously, we have talked about a lot on the thermodynamics and dynamics of supercooled liquids and glass forming materials, and we saw that as the temperature is approaching the glass transition, the dynamics include several orders of magnitude. By dynamics, I mean like the transport coefficient, like the viscosity or relaxation time or diffusion coefficient. All of them increase the many orders of magnitude. But it's natural to think about the structure. So in this slide, I show you that the structure factor of a binary Lagrange system at 3 different temperatures. So when I change the temperature, you see the structure factor of the material doesn't really change much. There's some small changes and very subtle. But the dynamics, like the relaxation time, changes from 9.2 to 25,000. It's many orders of magnitude. So this is actually the most challenging question, or I've said maybe the motivation to study supercooled liquids and glass transition. So how come the structure remains very similar, but the dynamics change to several orders of magnitude? In fact, the very influential coupling theory assumes that the structure factor doesn't change at all. But still, even if you keep the structure as a constant, by changing temperature or volume fraction, you can still find out why the relaxation time increased several orders of magnitude. Okay, so now I see another question. The question is the strong or fragile property related to the structure of the material, similar to the common sense of strong or fragile? Oh, okay. That's a different structure from this on this slide. Let me go back. So this so-called strong or fragile, actually, the reason why Austin Angel decided to use the word is what he meant is the local structure of the material. So when the local structure is formed in a liquid, how easy this local structure to deform? If the structure factor, if the local structure is very easy to break, then he called that fragile. If the local structure is very strong, like a silica, then the material is called strong. So it has nothing to do with our common sense of strong, of fragile of the material, but it has it's related to the strong or fragile of the local structure. Okay. Hope I answered your question. All right. So go back here. So in this slide, it's very significant. You can see that as the temperature changes very little, the structure doesn't change, but reaction time changes several magnitude. And I want to. Oh, the reason I want to show you this figure is also because this is something that we can measure with a neutron scattering experiment. As you have gone through the course, you know that we can detect the structure factor with a neutron diffraction experiment. Actually, in the next few slides, I want to show you some more phenomenon of the glass forming liquids or glasses, and most of the properties can be directly measured by neutron scattering. Okay. So the next striking behavior of a supercooled liquids and glass transition is the so-called multi-step non-exponential relaxations. So this figure plots the self-intermediate scattering function as of Qt, which can be measured from incoherent neutron scattering experiments. And we usually plot that in a log scale because it takes very long time. At low temperature, it takes very long time for these intermediate scattering function to decay to zero. So at high temperatures, you can see the relaxation behavior is very simple. It's a simple exponential, a so-called Debye-like relaxation. When the temperature is lowered, you can see the relaxation becomes the relaxation time becomes longer and longer. Not only that, the relaxation becomes non-exponential, and there could be multi-step relaxations. So this is also a very striking phenomenon that observed for glass-forming liquid from neutron scattering, from light scattering, including X-ray scattering. So, and for this non-exponential decay, oftentimes can be described with a kWw stretch exponential function. This basically assumes that the relaxation time has certain distribution. And when you measure the system, you average all different kind of distribution, and you end up with a stretch exponential. So in other words, the dynamics of the system is highly heterogeneous. So this spatially heterogeneous is also a very important concept in the study of supercooled liquid and glass transition. So we'll talk a little bit more in the next few slides. So and also this intermediate scattering function provides us an insight into what is going on at the atomic level when supercooled liquid form the glass. So at a very short time, you can see that the intermediate scattering function, or in other words, the density correlation functions, doesn't decay very much. This is basically the ballistic regions. And when we go to longer time at low temperatures, so there are two-step decays. So the slowest one is always called alpha relaxation, and the slow one is called beta relaxation. Okay, so the appearance of beta relaxation is very intriguing, and it's still well, we have a lot of explanations why this is happening, but still there's no agreement on like what is the final theory that should explain this multi-step non-exponential relaxations. So, like for example, in the case of decoupling theory, it explains that this is due to the caging. So, at low temperatures, all the items form cages. So, in order for one particle to relax or to diffuse, the cage has to break, and this will be related to the caging effect. Okay. Now I see another question from home. Why the question is why the relaxation time changes so much with respect to small change of temperature? Is there any proposed mechanism for this? That is the million-dollar question. So it's the key question to understand glass transition. So how come the relaxation time changes so many orders of magnitude with a very small change of temperature? And meanwhile, the structure of the material doesn't change much. So there are many. Is there any proposed mechanism? There are actually many mechanisms, and we'll we'll talk about that later on in this talk. Okay. So, so multiple relaxation, is one of the phenomena that happens while approaching the glass transition. And actually, there are many more happening. We'll go through them one by one. And the next one that I want to talk about is so-called decoupling phenomena, decoupling of multiple relaxation process. So this here, we have two relaxations. In this figure, I plot basically the relaxation time versus 1/t. And the slowest relaxation time is always called alpha, and the second slowest one is called beta relaxation. Okay, so it's pretty common that for glass-forming liquids, when it's approaching the glass transition temperature, the relaxation split into two processes, alpha and beta. And to make it clear, these alpha and beta are not exactly the same as the previous alpha and beta in the intermediate scattering function. So this relaxation time, this splitting of the alpha and beta relaxation time, is observed in the dielectric spectroscopy. Okay, and the decoupling also happens between the translational diffusion and viscosity. So the relation between the translational diffusion and viscosity is basically the Stokes-Einstein relation, and this is based on a hydrodynamic continuity. So at supercooled temperatures, because of these cooperated motions, the Stokes-Einstein relation also breaks down. So this is work by Professor Chen in 2006. So and what he did is measure relaxation time and also diffusion coefficient and try to test the Stokes-Einstein relation. So this result is very amazing because it demonstrates clearly at the crossover temperature, the Stokes-Einstein relation breaks down. Again, it's at the crossover temperature, not at the glass transition temperature. So many things has already happened above the glass transition temperature. Okay. And another interesting phenomena that happens above the glass transition temperature is so-called the Boson peak. So Boson peak is for many crystal materials, the full non-dense of state is basically G omega follows the omega square. So if you divide G omega by omega square, you should have a straight line. So for many glassy materials, if you measure full non-dense of state, you'll see that there's a bump, like here, the so-called Boson peak. So if we do neutron scattering, if we do incoherent neutron scattering, more specifically, what we can detect is SQ omega, dynamic structure factor. And in the small q limit, SQ omega is just proportional to G omega divided by omega square. So when we see a peak in the dynamic structure factor around this temperature range, it's oftentimes associated with a so-called boson peak. So all those phenomena happens around the crossover temperature and above above the glass transition temperature. And this is the temperature where we think the activated processes start to kick in. Okay. So now it's about time to talk about very important concept. So previously, in the last few slides, I have been talking about all different phenomena that we observe in glass forming liquids. So when approaching the glass transition temperature, okay, and most of the quantities that are selected here can be directly measured with neutron scattering. Okay, I mentioned that how to do that in the last few slides of this talk. So now the question is, how do we explain all these phenomena? Like what Hong has asked, what is the mechanism for those phenomena? So that comes to the theories of the glass transition. And actually, there are many theories. And people are always joking that the number of theories in this field is more than the number of people working in this field. So basic means that everyone has multiple theories. So, and here I want to start with a relatively generally accepted viewpoint. I wouldn't call that a theory because it's not a complete quantitative theory yet. So this is based on the energy landscape, and it's very intuitive. And at the very beginning of the talk, I showed you like one figure of the energy versus of generalized coordinate. to show you like the stability and metastability. And it's very natural to generalize this description into the higher dimension, into a many-body system. So that'd be so-called energy landscape. So we plot the potential energy as a function of all the coordinates of the system. So this will be like a very high-dimensional hypersurface. And the surface itself is rather complicated. Okay, but despite of this is a schematic drawing, but we don't know how to draw such a high-dimensional figure. And but it's natural to think using the energy landscape picture. So, for example, we always believe that the crystal is the lowest energy state. So it means that if you draw the whole potential energy, then there must be a very sharp and very deep minimum corresponding to the crystal. Okay, and but the energy landscape is rather complicated. We have a lot of small basins and big mega basins, and also there are a lot of saddle points. They're called the transition states. So this picture can qualitatively explain the phenomena we described in the previous slide, like the multiple relaxations, the fragility. So for example, the fragility, so for fragile material would be more like, actually for the strong material, the activation energy is basically constant, so it's corresponding to the jump between all these small basins. And for fragile material, the activation energy increases as the temperature lowered. This corresponds to the transition between these mega basins. Okay. So, in other words, the transition between mega basins corresponding to the alpha relaxation, and transitions within those small basins correspond to beta relaxations. So, this energy landscape, roughly speaking, gives us a very good explanation of the previous phenomena that we have talked about, like so here. So for strong material, then you can see the energy landscape is rough, but more or less with a constant activation energy. But for fragile material, the activation energy is temperature dependent. And the ideal glass corresponding to this transition that happens above the Haussmann temperature. And then we have very sharp crystals. Okay. So let me go back. So now again, so this is a very useful picture, and for us to have a physical intuition of what is going to happen near the glass transition. But in order to form a theory, we need a qualitative description of this energy landscape. So recently there are a lot of attempts on how to quantitatively calculate like the number of the minimum in this energy landscape. That can give you a more or less like a quantitative theory about glass transition. So okay, so next I want to move to a very important concept, so-called dynamic heterogeneity and cooperativity. So this is the probably the most popular opinion on the glass transition nowadays. So the people's picture on the glass transition is that at high temperatures, every particle just need to move by itself. But as temperature is lowered, depending on how you want to describe, in Moore-Kaplan theory picture, then for this particle, for this green particle to move, the surrounding particles might need to open this cage. So in order for the relaxation to happen, several particles needs to rearrange together for one particle to relax. So this can give rise to the slow dynamics. And the Moore-Kaplan called that cage effect or hopping mechanism. If you look at only one item, if you look at this rearrangement themselves, then they are called dynamic heterogeneity. The dynamic heterogeneity refers to, like in this picture, shows like the trajectory of a two-dimensional particle movement within like the relaxation time range. So you can see that there are spatially separated regions with very different dynamics. Okay? Or in other words, dynamic heterogeneity is also called spatially heterogeneous dynamics. So the picture of the glass transition is at high temperatures, dynamic heterogeneity doesn't occur. But once the temperature is lowered, the dynamic heterogeneity of this region start to increase. So eventually, at idealized glass transition temperature, so in order for the total system to relax, every particle has to coordinate with each other, and they can. So in order for everyone to cooperate, and that is the so-called idealized glass transition. So, and before the glass transition happens, this dynamic heterogeneity refers to an intermediate length scale and intermediate time scale phenomenon. Okay. And you can also see that in order to quantify the dynamic heterogeneity, well, there are many properties that are proposed, but you can actually already see that from the mean square displacement, which can also be determined by neutron scattering experiment. The mean square displacement as a function of time. So at very long time, all the particles diffuse, so mean square displacement follows the Einstein diffusion law. At very low time, very small time, so the particle is basically just rattling at its in the cage surrounded by its neighbors. So as the temperature is lowered, there's this intermediate time range, an intermediate length scale feature that's corresponding to this dynamic heterogeneity. And the next quantity that is often used to quantify the dynamic heterogeneity is the non-Gaussian parameter, which is basically the next order term of the mean square displacement. So if the liquid is not heterogeneous, if the diffusion is just pure Debye-like exponential, then the non-Gaussian parameter basically should be 0. Okay. But in supercooled liquid, as the temperature is cooled, you can see that the system becomes more and more non-Gaussian. So the peak of this alpha 2 can be used to quantify such a size of the dynamic heterogeneity as the temperature is lowered. Okay. So more recently, people have been proposed in order to really quantify the dynamic heterogeneity, we have to go to the 4-point correlation functions, or the multi-point correlation functions. It behaves very similar to the alpha 2. So this is our simulations on water. You can see that at high temperatures, this chi4 is very small. As the temperature is lowered, then the maximum as chi4 basically increase and increase. So that this chi4 is proposed to quantify this dynamic heterogeneity in supercooled liquids. So the key question or the key experimental challenge is that chi4 is a 4-point correlation function. So in experiments, we can only probe, well, by doing a scattering experiment or perturbation experiment. Because of the linear response theory, we can only have a 2-point correlation function. So there's, in principle, determining a chi4 would be difficult. So actually, I'm trying to develop methods combining computer simulations and neutron scattering to try to determine such a function experimentally. Okay. So another way to access chi4 from experiments is by look at the so-called dynamic susceptibility. So again, because of chi4 cannot be directly determined from the scattering experiment, but what we can do is determine the intermediate scattering function, which is again like a it's not called chi2, but it's basically a 2-point correlation function. So recently, people have proposed that if we know this 2-point correlation function here, f, and vary certain control variable of the system, like x here, either temperature or pressure or volume fraction, etc., we can use this so-called dynamic susceptibility to estimate the lower bound of the 4-point correlation function. So in this slide, let's show you like the estimated 4-point correlation function from experiments. So the first one, A, is chi t. So it's basically the temperature derivative of the intermediate scattering function. The second one is chi phi with respect to volume fraction. So this approach is very significant because it gives us a way to estimate the 4-point correlation function. Although it's not a direct probe, but we can already estimate lower bound. So another disadvantage of this method, or maybe not disadvantage, but a concern would be, so this inequality relies on the fluctuation dissipation theorem. So that is known to be to break down at certain temperature when approaching the glass transition. So this kind of descriptions works in the supercooled regime and maybe even near the crossover temperature. But eventually, this kind of formalism may break down. So it is a big challenge, like how to really quantify the 4-point correlation functions directly from scattering experiments. Okay, so all of those are open questions. So now let me try to spend a few minutes try to review some basic theories of glasses. And again, the number of theories of glasses are so many that we cannot cover all of them. But a few important ones are like are listed here. The first one I want to mention is so-called Adam-Gibbs theory. So Adam-Gibbs theory considers this the concept is very similar to the dynamic heterogeneity. So consider these regions that several particles need to rearrange themselves. So according to the theory, then the activation energy should be inverse proportional to the configurational entropy of the system. Okay, and then the relaxation time goes to this, like a Arrhenius behavior. So Adam-Gibbs theory works very well. Above the glass transition temperature is widely used. And the next theory that I want to talk about is so-called free volume theory. So free volume theory was described a long time ago, and the opinion is almost the opposite of the Adam-Gibbs picture. So in free volume theory, the activation energy is assumed to be inverse proportional to the so-called free volume. So in this picture, the free volume picture, we consider more like each individual particle instead of this region of particles that have similar dynamics. So in free volume theory, we consider like how much free volume does one particle have. So at temperature is lowered, then the free volume, the volume that is free for the particle, becomes decreasing. So that gives rise to the increase of the activation energy. Okay. So the free volume basically decreases as the temperature decreases. So this theory can also explain some features of the glass transition, or like the change of the relaxation time. Okay, and the next theory that I want to mention is so-called Multistep theory. So this is probably the most influential theory of glasses, and the reason is that this theory describes this f of kt, which is the so-called intermediate scattering function or density correlation function that can be directly determined from scattering experiment, from neutron, from X-ray, from light. So this theory based on a generalized Langevin equation, and so this damping term is included as a convolution between certain memory kernel and the intermediate scattering function that considers the memory effect of the material. So Multistep theory uses a structure factor as the input. So there's no change in the structure factor during the glass transition. But based on this formalism, the relaxation time, well, this theory is very successful in describing like the bifurcation of the alpha and beta relaxation time, and also the non-exponential, so the kW back to like a static exponential decay and many scaling behavior. So, but the downside of the theory, the idealized Multistep theory, is that it predicts a true ergodic to non-ergodic transition. So there's a really structural rest phenomenon. But in practice, we know that even below the glass transition temperature, there's still some kind of relaxations. Although slow, but there are still some relaxations. So because of this activated process. So after this theory was formulated, there have been a lot of attempts try to modify the memory kernel that take into account this activated process, the so-called hopping process. Okay. So, but then the theory becomes much more complicated and relies on many parameters. Okay. So, and another opinion of the glass transition, well, there's a series of theories, all of them based on frustration. The basic idea is that for liquid to crystallize or to form a glass, they have some locally preferred order. So they have so particles tend to form a local order at a very short length scale. But those local order, locally ordered structure cannot tile the entire space. For example, if it's a local preferred structure is a tetrahedral, we cannot tile the entire space with a tetrahedral. So there's an intrinsic incompatibility between the local packing and global packing. And in order for the system find out the global packing, then takes very long time to happen. So this also gives rise to the relaxation, the very slow relaxations. So, and another theory is it's not directly related to glass transition, but concept is very similar to the dynamic heterogeneity. This is a so-called STZ theory, shear transformation zone theory, the plasticity of non-crystalline materials. So this theory basically assumes that in order for the materials to have a deformation, there exists certain separated shear transformation zones. Okay, and conceptually, it's very similar to the dynamic heterogeneity. Okay. So, and also, just random first order phase transition tries to set up this theory basically focuses on the entropic force of glasses, and the trajectory space theory basically describes the glass transition instead of real space, but in the trajectory space, and found out glass transition is a first order phase transition in the trajectory space, and so on. And in the end, I want to mention this energy landscape again. Okay. So in the last few minutes, so I want to talk about neutron scattering. So, and how neutron scattering can be used to study liquids and gases. So you probably have seen this figure again and again in this course. So neutron scattering basically uses incident neutron, heat the sample, and we detect the scattered energy and momentum. Then we can calculate energy transfer and momentum transfer. So at the end of the day, for the interaction here, you can choose a Fermi pseudopotential and find out double differential cross-section. At the end of the day, this is the only formula, very simple formula that you need to remember. So what you detect is this double differential cross-section. It's basically a sum of two terms. One is the coherent dynamic structure factor. The other is the incoherent dynamic structure factor. And so the coherent dynamic structure factor is basically a Fourier transform of this coherent intermediate scattering function. The same thing for the incoherent, and that's a Fourier transform of the self-intermediate scattering function. So a lot of the theories, especially the mode coupling theory, are based on these intermediate scattering functions. So now you can see that why neutron scattering has played and will continue to play a very unique role in the study of liquids. So actually, a lot of pioneers in the liquid state physics are neutron scatterers, like Peter Eagle's stuff. So now we can see that the neutron scattering basically proves is the so-called intermediate scattering function is nothing but a density correlation. It's also density correlation. They only depend on, well, density, I mean the number density. So they only depend on the location of the atom, Ri. as a function of t. And that's the reason why you can easily compare the neutron scattering result with the computer simulations. And the test is exactly one-to-one. So what we can measure from neutron scattering experiments can be directly calculated from computer simulations. Okay, and this quantity is a density correlation. So in other words, neutron scattering basically proves the fluctuations between the fluctuations in space and time. So if there's no fluctuations, then there's no scattering, there's no contrast, there's no scattering. Suppose if a material is continuous, is homogeneous, then you won't be able to detect any scatter pattern. Or if your material doesn't fluctuate with time, then you cannot prove any dynamics. Okay. So now, why are neutrons useful to study liquids? So I want to list a few quantities that we can measure from neutron scattering. Okay. So by doing diffraction, well, you've seen this many times throughout the course. So first, we can do diffraction. By doing diffraction, we can detect the structure factor, or basically it's a Fourier transform, a pair distribution function that describes the structure of the liquid. Now we know that in the study of supercooled liquid glass transition, the structure factor doesn't really change much. So if the system is very big, then we can go to very small angle, so-called small angle neutron scattering that can give us the information of large scale structure. So this is very useful to study like colloids, polymers, or biomaterials that are relatively large compared to atoms and molecules. So we also have a neutron reflectometry. With this technique, we can study like a liquid interface. And more importantly, with neutrons, we can do inelastic measurement. Okay? So with other techniques like X-rays, we can do photon correlation spectroscopy. So we will be similar to this quasi-elastic neutron scatterings, but for X-rays, the Q range and the time range are very different from neutrons. Neutrons is very natural to study dynamics because the neutrons has the energy very similar to the fundamental excitations of the materials. So it's much easier to detect such energy transfer with neutrons. So for example, if you use a thermal neutron with or cold neutrons, the energy of neutrons is milli-electron volts. So, and the fundamental excitation of the material is also in the range of milli-electron volts. But for X-ray, we have to use like KeV X-ray. So we need an ultra high resolution X-ray to do the measurement. Okay. So by doing quasi-elastic neutron scattering, so for quasi-elastic, so we basically detect the very small energy transfer near the elastic line. The very small energy transfer corresponding to the slow relaxation. And we can use the neutron spin echo and detect the intermediate scattering function directly. And by doing a coherent inelastic neutron scattering, we can detect the fundamental excitations like the phonon dispersions. And by doing incoherent scattering, we can directly detect the phonon length of state. Okay. So in the end, I want to mention that glasses are very complicated. There are multiple routes to form a glass. So cooling, or so-called quenching, is only it's one of the ways to form a glass. Or you can also use like a vapor deposition, or at cold temperature you can compress a crystal to form a non-crystalline state, or you can even use a radiation to vitrify the material. Okay, so glass is a rather complicated subject. So I want to basically conclude from actually a local expert. He spent his childhood in Urbana-Champaign, and he's famous Philip Anderson. So he said the deepest and most interesting unsolved problem in solid state theory is probably the theory of the nature of glass and the glass transition. So in the end, one more slide. So glasses is really, as I have demonstrated, it's really a non-equilibrium system. So in nature there are many different phenomena happen far from equilibrium. So in this slide I show you like all different patterns of amazing complexity generated spanning a very large time and range scale. So this is the plasma turbulence near the sun, the water stress corrosion cracking, and the spot of aperture, and the rust, crumpled paper, the fracture of glasses, and jamming. So all of these are far from equilibrium phenomena. So studying glasses or glasses soft matters can help us to identify the role of randomness and the role of fluctuating degree freedoms in the organization and transport of energy, momentum, and matter. So by that, I want to conclude. The take-home message is liquid state physics is intriguing and still waiting to be explored. And supercooled liquids and glass transformation is a model system to study far from equilibrium phenomena. And last, neutron scattering is incredibly useful to study this problem. So by that, I thank you for your attention. I'll be happy to answer your questions. Okay, I see one question. The question is, experimentally, how long per degree you cool the water to get a glass state? Okay, and the second question, let me answer this one first. So, well, there are many ways to vitrify water. So you can do that very, very fast, or you can do that slowly, as I have demonstrated. So for backwater, you don't really have you don't really need a very fast cooling rate to get the supercooled state. But in order to get the glassy state, then you need to cool really fast. So what we were doing is actually, well, since we just listened, thanks to Jin's nice lecture, so we're trying to locate whether there's a second liquid to liquid critical point in water. So, and based on his theoretical predictions, the second critical point lies in the region of the phase diagram, that's so-called no man's land, below the homogeneous nucleation. So there's no way for us to maintain a supercooled water experimentally in that region. So we use nanopores. So we can find water in the nanopores. So in other words, when we do that, water does not freeze in that conditions, and you are safe to do whatever cooling that you want. So second question is, do you think we can get glass state of water if we cool 30 minutes per degree? Probably not. So again, this is a 13 minutes per degree. We can get a supercooled state, but not the glassy state because of the homogeneous nucleation. So unless you cool really, really fast, you won't be able to get the glassy state of water. And it's very difficult. And in fact, the true glass transition temperature of water is still a matter of argument. Okay, the next question is, why are high temperature systems more ergodic than low temperature ones? So the question is, why are high temperature systems more ergodic than low temperature one? So high temperatures, each particle has a higher energy on average. So temperature is a very kinetic energy. So the system can easily sample the whole phase space. At low temperatures, because the kinetic is very, very slow, so in order for the system to sample all the phase state, it take a very, very long time. So the system gets trapped into some local state. So that's why high temperature systems are more ergodic. Continue my question. If we cool it 30 minutes per degree, so what you really mean is like 30 degree per minute, am I right? In confined situation, such as a nanometer scale. Yeah, 30 minutes per degree is very slow. All right. Well, thank you very much for your attention. So if you have any questions, you can find my email, shoot me an email. So I'll be always happy to interact with them. Thank you very much, Mei Yun. Thank you very much, Jin.